Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 31st, 2025, just 2 days ago. It introduces a method that speeds up video generation by 1.65 times and reduces compute by about 57%, all while maintaining the high visual quality of large models. The paper is titled FlowBlending, Stage-Aware, Multi-Model Sampling for Fast and High-Fidelity Video Generation. And as we'll see later, the results for combining this with other acceleration techniques are quite significant. Figure 1 illustrates how FlowBlending combines the strengths of large and small models to optimize video generation. The top row shows a small model. It is fast at 3.1 petaflops, but it fails to capture complex prompts, like the Van Gogh style. The middle row uses a large model, which nails the details but costs 30 petaflops. Finally, the bottom row shows FlowBlending. This approach employs a large model only for the critical start and end stages, effectively matching the high quality of the large model, while cutting compute to 19.2 petaflops. So, Figure 2 breaks down why the early stage is so critical. The top row shows runs, starting with the large model. Notice that the mix schedule on the right looks nearly identical to the large baseline on the left. This confirms that once the large model sets the structure, the small model can take over safely. In contrast, the bottom row starts with the small model. Both the all-small run and the small then large run fail completely, producing a tangled green mess. This proves that if the initial structure is weak, adding capacity later cannot fix it. While Figure 2 just gave us the visual proof, Table 1 now quantifies exactly how much better the early large schedule really is. The second row highlights the LSS strategy, which starts large and then switches to small. It maintains nearly 96% dyno similarity and 97% clip similarity to the large-only baseline, effectively preserving the intended content. In contrast, the bottom rows reveal that starting with the small model causes a massive drop in quality. Both the SLL and SSS schedules plummet to around 65% similarity, confirming that a weak start is unrecoverable. Okay, Figure 6 reveals the mathematical justification for this schedule by tracking velocity divergence, which essentially measures how much the large and small models disagree on the next update. On the left for WAN 2.1 and on the right for LTX-Video, we see a consistent U-shaped pattern. The divergence spikes at the start and end, indicating that the models strongly disagree on structure and fine details, which confirms why the large model is needed there. However, in the wide intermediate section between the red arrows, the curve flattens out because the small model's predictions are nearly identical to the large models, making it safe to switch. Well, Figure 6 gave us the theory, and Table 2 delivers the hard numbers. In the top section for LTX-Video, the second row highlights the stage-aware large-small-large strategy. It maintains a Frechet inception distance of 5.70, effectively matching the large-only baseline directly above it. Yet, looking at the efficiency columns on the far right, runtime drops from roughly 50 seconds to 30, and compute falls to about 2,000 teraflops, proving we can cut costs nearly in half without losing quality. So, Figure 7 expands this view by plotting quality versus cost for nearly every possible schedule. On the left graph, which tracks FID scores where lower is better, notice the cluster of blue dots at the top. These represent schedules starting with the small model, and their high placement signals poor quality. In contrast, the yellow star for FlowBlending sits much lower, matching the all-large baseline in red, but with far less compute. The right graph confirms this for motion smoothness, where higher is better. Here, the blue dots plummet to the bottom, while the yellow star remains high, proving that a strong start is essential for both static quality and temporal coherence. Wrapping up, 2 takeaways stand out. Model capacity is not equally important at every step, with the heavy lifting really only needed at the start and end. This means we can achieve high-fidelity video generation with significantly less compute by just strategically blending models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.